Because we got a speaker from abroad, Simon Vergauwen, came all the way from Brussels to give us a talk about Kotlin. So Kotlin is a language we typically do not talk about much in our meetup. So far it's been mostly Scala. But Simon is an exceptional Kotlin contributor. He has been maintaining the Arrow library, which is a functional addition to the standard Kotlin features. So in the first part of his presentation, he will talk us through the arrow effects, the functional extension, and he will cover the basics, but he also touches upon advanced topics such as performance considerations. And in the second part of the topic of his talk, he will present Arrow's Meta, which is a metaprogramming library, which I'm sure many of you will find interesting to hear what you can do with the compiler, Kotlin compiler, and how you can enhance it. So without further ado, let me invite Simon Vergauwen on stage, and that stage is yours, Simon. Thank you.
So first of all, I want to thank the meetup for inviting me here and everybody for showing up tonight. And before I get started, I want to get a little bit of feel of the audience because this is a functional meetup. So how many of you are using Kotlin, either professionally or in their spare time? Okay, quite some people. How many people are using Scala? And are you using functional Scala, type level Scala stuff? Okay, cool. Any Clojure or Haskell or anything else here? Okay, cool. So without further ado, I'm just gonna dive right in. What is arrow effects? But first I'm gonna do a small introduction about myself. So I'm Simon. I work remotely for 47 degrees from Belgium. And I joined Arrow when I built an optics library in Kotlin. And I then joined forces with a library which we still called category. And there was another library in the Kotlin ecosystem called functionality. And because we did not want these competing libraries within the same language ecosystem, we joined forces with them, and that is how Arrow came to life. So I'm mostly known in Arrow for my work on Arrow optics and my work on Arrow effects. So effectful programming and determinism. Before we dive into the stuff, I just want to do a real recap of what is effectful programming, what is determinism, what is purity, for those people that are not super familiar with that. So the majority of our programs contain side effects or uncontrolled effects, such as query to the database, performing network requests, printing to the console, drawing a UI. All those kind of things are unpredictable. And so we want to have more control over them so we can reason better with them. So as I already said, uncontrolled effects result in unexpected results whenever we run that effect, and that results in non-deterministic programs. And it is something that we would like to avoid. But can we really completely avoid it? Because we do need side effects to build meaningful programs. Just like I just mentioned, side effects are things like querying the database, drawing a UI, interacting with the user, commuting over the network. Those are things that make our programs meaningful, so we cannot avoid them. So how can we stay deterministic? First of all, the thing we want to do is we want to push all this stuff to the edge of the world. What does that mean? That means that in your program, you actually only once run your side effects. This on Android could, for example, be the application, a view, or an activity. On backends, this could be the API endpoints, or in other programs, this could be the main function. So now, what is a pure function? What makes a function deterministic? A function is deterministic or referential transparent when for the same given inputs, it results the same output without making an observable change to the world. And that is actually quite important to know here because there's a bunch of functions I can write that always result the same output, but they still do something else. They could change a state on the server, they could change something in the database while still always yielding the same result. So those are things we also want to avoid. So first question, is this a pure function based on the story that I just told you? The answer is no, because if I want to print a result, I'm also going to see hello world. So there is clearly an observable side effect in the world going on here because we changed what was on the console, which was our actual function, and we were actually just expecting the result of that function. So here we were expecting only unit because that is what we assigned to result, but as a side effect, that function also ran. So that is something that we want to avoid. So how can we avoid that? For example, we could wrap our side effects in I/O. Right? I/O, you cannot run I/O, and if we run this program, you will see that it just returns a data structure. So no side effect actually happened. The I/O effect I have here just builds a data structure, and that's it. So it's a pure value, and no side effect or no observable changes have happened. So this is a little bit of a trick question, especially for the people that don't know Kotlin. Is this a pure function? It is a pure function because we marked it with suspend. So if I try to run this function, the output will actually say, oh, there is no output, because the compiler will actually tell us you cannot run the suspend function outside of a controlled environment. Similar to how you cannot run I/O anywhere, you can only run I/O in a controlled environment. You can only run suspend functions in a controlled environment. But that actually gives us something pretty cool because Kotlin also has a suspend main function similar to Haskell's main I/O unit function, which means that now this program is 100% pure. My side effect function was marked with suspend, which means that it is a pure function. It cannot be run outside of a controlled environment. My main function is also suspend, which means it also cannot run out of a controlled environment. And the Kotlin language will take care of it for us to run the suspend function in the correct way, depending on what platform you're building your program for. This could be JavaScript native or the JVM. So just to quickly show this prints hello world. So now we have 100% pure hello world program, similar to putstring hello world in Haskell. So how does the suspend business work? Because what is this magic in the compiler? So actually the suspend gets rewritten to a callback, which is a continuation. That continuation has a coroutine context, and it has a resume with function. That allows us to write these kind of affecting functions in a sequential way, because the compiler will hide the callback help from us, and it will actually transform our imperative code to a callback-based one. And then an additional very powerful thing in the Kotlin language with suspend is that restricts suspension. And this actually allows us to give more power to the suspend keyword. Because as I already mentioned, suspend can only run within another suspend function on a controlled environment like IO effect. But we can also limit some functions being run even within those controlled environments. For example, you could build a database class or with database context, and within that database context, you're only allowed to run database functions. So how do we achieve this? I'm not sure if it's super visible on the slides, but above this class, there's an annotation restricted suspension. And what that does is that means that within the restricted class, we can only call suspend functions that were defined for restricted. So here in the top, we define two functions. One is suspend print hello world, and it is not defined for restricted. The other one is defined for restricted, as you can see here. And for the non-Kotlin people, this is a receiver, which means that the compiler transforms this to a first argument. And this means that this function is also defined for restricted within the Kotlin language. And for that reason, in the fun X and fun I below, print hello world 2 will actually compile because it is defined on restricted, but the other one will not. This means that we have a mechanism using suspend and restrict suspension to build certain things, which I will show you in a minute, where you're allowed to call certain functions and you cannot call certain functions. And this concept is extremely powerful because it allows us allows us to do effect tracking within Kotlin. So suspend an arrow is arrow effects. And the goal of arrow effects is to build a purely functional effects library for Kotlin. So as already mentioned, it's an accompanying library to the standard library of Kotlin. And it has an emphasis in empowering simple and declarative effects for programming. And the reason that we want to focus on that so bad is because the premise of Kotlin, or the premise from suspend, was that we can write async code or complex callback code in an imperative way. So our goal with arrow effects was to also bring all these functional features, all the safety you get from functional programming to the Kotlin language without all the overhead that we're used to from other places. So the arrow effects library exists out of 4 building blocks. The effects blocks, which is a scope block. Within that, you do all your work. It is an effect function, which you use to affect side effects, and nothing else but the side effects can be wrapped. We have the bang operator, which is similar to the arrow in the 4 comprehensions, or do notation from Haskell, where you can extract to the left-hand side. And then we have an unsafe operator to run your unsafe side effects. So let's take a quick example. So here we are opening an effects block for I/O. And within the effects block for I/O, we're calling print hello world, which is a suspend function. Like I already mentioned, side effects needs to be wrapped within effect, or you're not allowed to call them. So this is the mechanism that we've achieved with the restricted suspension that I just mentioned. And we can disallow suspend functions being called within our block. So it is actually required, if you want to run side effects, to wrap them in effect. This is how we have achieved effect tracking, because we can disallow side effects to just run in the while. And as I also already mentioned, this bang operator, similar to Scala 4 comprehensions or Haskell do notation, allow you to extract the value to the left-hand side while staying pure within the effects block. And this allows us basically to get rid of all this nested flatmap calls and rewrite things to 4 comprehensions or do notation. So we achieve this imperative style of coding and getting rid of this callback-based way of coding. And in this slide is subject to change. As you've already seen, since the last version of Kotlin, or one of the last versions of Kotlin, we have support for suspend main. Currently, we still rely on an unsafe type class, but this will probably be or might be replaced with a combination of suspend and unsafe for cancellation. That is still something in the works, which will be released in one of the next versions. But to just showcase here, instead of using unsafe run sync like you would do on I/O in Scala, you open an unsafe blocking, you can call the run blocking method, or the run non-blocking, which is unsafe run async. And here's where all the interesting stuff comes. So arrow effects comes with a bunch of concurrency and parallelism tools. This is what gives you this powerful imperative style of programming. For example, here we can call continue on to switch contexts, which is a very popular thing on Android in the front end that I know from experience. And this allows you to change threads or execution context in an imperative way. So here, if we run this snippet, then we can see that we move from computation, then we go to blocking I/O, and then we go to the UI thread. Then it was as simple as just writing inline continue all functions. But arrow effects also has the concept of fibers that some of you might know from Cats effects or ZIO. And fibers are lightweight async processes that you can run. So here's an example, and we have a very simple effect that prints the thread name, and we're going to fork it, which gives us back a fiber. And this fiber is basically a join and a cancel operation. So this join operation, you can just use it as you would regularly use, and no matter how many times you join, this effect is only run once. So basically, you can see a fiber as it runs your program or your effect on a certain context, and then it yields the result in a promise. So the fiber is never run more than once. But of course, dealing with errors in async processes is a little bit annoying, especially if you're not using concepts like these. But fibers are very powerful, and they will actually take care of all of this for you. And with using this effect, even in an async effect, the exception will be maintained and it will pass to you later on, so you can do your error handling just like every other way that you were used to from before, if you were working without fibers. So here, as you can see, I have a fiber that immediately blows up, and I can very simply recover with handle error with that most of you are probably familiar with. Another cool thing about Arrow's I.O. is that it has built-in cancellation. So similar to Katz effects, if I'm not mistaken, a flat map is a cancellation boundary. So if you're using or you're building your programs with I.O., you're also automatically cancelable. At this point in time, with the current Arrow release, every flat map boundary is still a cancellation boundary, but this will become configurable in the future. So to just give you a quick demonstration, this job was running infinitely and it stopped after 100 milliseconds. And to show you I'm not cheating, there's an infinite loop that just sleeps for 10 milliseconds and prints something and then infinitely loops back. So as I already mentioned, cancellations and async errors can be extremely tricky to deal with. And this is why we have bracket, which most of you are probably also familiar with. So the problem that brackets solves are actually multiple problems. First of all, if you're trying to do try-catch across async jumps, that's never going to work. Because if an exception happens on the first thread, and you then move to the second thread, the stack exception will stay in the first stack of that first thread. So the second thread will never see the error. Bracket takes care of this for you, similar to fiber, and it brings the error for you from the one stack frame to the other one. So this means that we can compose very powerful effects or I/O effects, concurrent effects, and still deal with them in a resource-safe way. So as you can see here, the file contains some interesting content, and it was closed successfully. Now, the snippet for cancellation is a little bit more tricky, but I can show you this snippet for when something goes wrong. So let's say that I acquire my file, and then I want to use it, but I immediately throw an exception. Then before that exception lands in my actual program, or it actually blows up my program, because I did not deal with my error here, the file is still closed. And the same happens with cancellation. So bracket allows you to combine very powerful programs and still deal with resources in a safe way. For example, in this case, you will probably want to open a file on an I/O context, and you want to process the file in a computation context, and then you might want to come back to UI context to drive some results on the screen. Something like that. So everything we've seen before is mostly concurrent operators, but we also have a bunch of parallel operators, and I'm not going to cover everything, but I'm going to cover some of my favorite ones. We have race n, which has support for racing for n arity. And the cool thing here is these things are always wired correctly for both cancellation and error handling. So for example, let's say that you want to cancel the race, then all the participants get canceled. If one of the participants wins, then the other will be canceled, because there is no need to keep running the program if you have already decided who the winner was. There are other operators that allow you to receive this ongoing operations that did not win. But in this example, I think it's a very powerful one. You can just raise some operations, and I only care about the winner. Another one of my very one of my favorite operators is power map. I use this one a lot, and it allows you to run a bunch of programs in parallel and then combine the results. So I'm sure this is nothing shocking to anyone. But as you can see here, I'm just printing three thread names, putting them in a tuple, I'm destructuring them, and then I'm printing them afterwards. And of course, just like fibers and all parallel stuff, things can go wrong. And like I already mentioned, the powerful thing about arrow effects and these kind of libraries is that they wired all the difficult stuff already for you. So all this error wiring between parallel or concurrent operations and cancellation, that stuff is all already done for you. Which are, in my opinion, some of the most difficult things to implement. And then the last parallel operator I want to show today is part traverse, which is also a very commonly used operator. So part traverse, you can use it to traverse over any kind of container. I'm using in this case list, but this could be any other container, as this is all functionality that is under the hood enabled by type classes. So you could just use it for set or map or whatever you want, as long as there's a traverse instance. And here I can traverse the list, and for every element in the list, I'm gonna print a number and I'm gonna point on what worker thread it worked. And there are a bunch of more parallel and concurrent operations, but there were way too much to cover here all today. To give some examples, there's parse sequence, which we'll also see in the slides. There is sleeping, there is timeouts, there's other kind of racing operators. You can derive a timer instance or a par applicative instance from concurrent. So all those super advanced stuff is also already there, but that was too much to cover today. It is all documented, so I invite you to check out the ArrowFX website if you are interested. But ArrowFX also comes with a bunch of concurrency primitives that some of you might be familiar with from Katz effects or Haskell or ZIO. So the first one I want to show here today is promise. And the cool thing about all these concurrency primitives is that they're all semantically blocking. So they all do what you want them to do out of the box. In this case, I'm simply creating a promise for I/O, and I'm going to have two competitors, and they're going to try and complete the promise as fast as possible, and I'm going to run all of this in parallel. And I'm also in parallel going to run an operation that gets the value from the promise and then prints the winner. So as you can see here, the first winner won. But this is actually a little bit different with all the functional libraries. For example, if you had them try and complete, we would get an exception because you cannot complete a promise twice. So that is something that you have to deal with. But we also have a save operator for that try complete. Then the next one is an atomic reference. So an atomic reference, and all these concurrency primitives are built because they have API specific for I/O. So if you could also use an atomic reference from Java, but it would be extremely annoying to work with all your I/O operations. So in this case, we can create an atomic ref, which was built for our functional framework. And we can update this ref twice, and we are always sure that this happens in an atomically correct way, which is what you want in a parallel environment or a concurrent environment. And it's a little bit sad because it seems like the backend where I'm sending these snippets to yields the same result quite often. Maybe the sample set is not big enough with just two concurrent operations, but I'm sorry about that. And one of my favorite, very powerful, it took me quite a while to grasp, semaphore. Semaphore is a very powerful concurrency primitive because it allows you to do very powerful things. And in my opinion, it scales. It helped me scale very well. For example, here I have a list with 4 tasks, and I'm going to run them in parallel with parse sequence. And there's a couple of things that I could do to limit only 2 of the 4 tasks running at once. So you could do this with a special execution context that only has 2 workers, so there's only 2 things happening at the same time. But you might as well just create a semaphore which only has 2 permits, and then you can say whenever you want to execute this task, you have to do it with a permit. And now I can just compose this around my original effect, and I can now run it in parallel. Only 2 tasks I can run in parallel because the semaphore only has 2 permits. And we can parameterize this, and depending on what device or on what server you're running your scripts or your program, you can very easily scale in size. For a more powerful machine with more memory, you can run a much bigger amount of tasks in parallel than on my small computer over here. So again, this is a little bit sad because I cannot show it live. The playground sends the whole output back together. But trust me, these tasks, they run 2 at a time. And then the previous to last concurrency primitive mvar, which a lot of people might be familiar with, it's a queue. It's with a single capacity, and all the operations here are blocking. So in the first line, I'm trying to put 3 values in the mvar, but it only accepts 1 value, so the other 2 values will block until the values were consumed. And then on the line, and I'm forking this parallel operation. So on the line below, I can take the values 1 per 1 from the mvar. And as you can see, due to concurrency and the parallelism, this time they didn't end up in the same order as we saw them above. And if I'm lucky, it changed again. So there is proven that this stuff is all working in parallel. And then I want to mention something else, something that I was personally very excited about. In the next ErrorFX release, there is also Q coming, or at least bounded Q, which was contributed by Richard Gibson. The PR is open right now. It was ready for review and will be probably merged this week. So there's still a lot of heavy development going into ErrorFX. But at this point, you can almost already do anything that you would be familiar with from other frameworks or libraries. And then one last thing I want to show, which is one of my favorite things. The FX DSL that we've just been discussing is the exact same DSL concretely for I/O or for any other concrete data type as it is for the tagless alternative of that program. So this is just a program that I copy-pasted from a couple of slides ago. So if you can see here, I created a ref with an empty list. I did 2 operations on parse sequence, and then below I got the reference from the ref. So without changing any of that code, I now have a final tagless code written for F based on the concurrent type class. And the code within the FX block is exactly the same. And it is actually so powerful that it didn't even have to add or remove any imports. I'm not going to get into detail how that works with the imports because this is something very low-level Kotlin specific. If you're interested, feel free to ask me after the talk. But this way, you can very easily refactor your I/O programs to tagless programs with almost no effort. Another cool is we're bringing effects to all the monads, so not just to the effectful monads. The difference there is you will only get the power available to you according to your highest type class. So it makes perfect sense that for option, we will not find par traverse or par map because option is not capable of doing those kinds of operation. But we can use effects similar to for comprehensions, for option, IDEA, eval, and all the other data types that you're familiar with. There's a couple examples how it looks for the different monads. And then one last thing I want to talk about here is performance. Coming from an Android background and a JVM background, There's a lot of concern about functional programming because there's too much wrapping, and all this wrapping allocates memory and slows down the program. But it also has a lot of benefits, and that's probably why we're all here. So just I want to make a comparison between this program, which is a lazy Fibonacci sequence written for I/O, and then the same program rewritten with suspend. As I already mentioned earlier, suspend can also not be run outside of a controlled environment, which means that suspend is actually isomorphic to I/O. But since we can write suspend in the direct style, we can also use tail recursion together with suspend. So by using tail recursion together with suspend, we actually have a pure function, but there is no wrapping whatsoever going on. And if we prepare these two styles in comparison, we can see that I/O only has 547 operations per second, and the direct style has a whopping 16 million operations per second. So that's quite the difference. So why is this important, and why would you still use I/O? This is neglectable and effectful programming. If you're contacting the network, if you're doing a query over the database, nobody is going to be worried that you're creating a data structure to wrap your effect. But if you're doing something like a Fibonacci sequence, where things are amazingly fast, there's no need to wrap everything in I/O because it will just slow you down. But you still might want to keep that purity, so you can very easily refactor those problematic places in your code base that are too slow, make them suspend, and you can still integrate them with I/O, and you can still benefit from all the functional benefits. You can still program in a purely functional way. So I would ask everyone here to join us. We're on GitHub, we're on Slack, and we're also on Gitter. We're a very friendly community. We love helping new contributors. We also give one-on-one guidance to new contributors if needed. So definitely check us out. If you have any questions, be sure to swing by there. And I want to thank 47 Degrees for sponsoring and pushing the development of Arrow. And I also want to thank everyone that made Arrow possible. We're currently over 150 contributors, which I think is amazing. So I want to thank everyone that made this help become possible. Are there any questions? Yes?
Hi, thank you for presentation. Thank you for your presentation. My question is, how do you test the code? Do you have some, like, I don't know, special tooling for testing concurrent stuff, or do you somehow...
Really hard time understanding your question, sorry.
If you are using some special tooling for testing, if you test concurrency, is there some tooling to test that is working somewhere?
So the question is about tooling, whether they're concurrency testing, etc.
Okay, so there is no special tooling available. There is some tooling available in IntelliJ for debugging concurrency stuff, which is universal to all languages. If you're thinking about something specific like ZIO has, that is not available yet, but we would love to have something like that in ArrowFX. I'm not sure if I answered your question correctly though, or if that was your question.
So could you show me some of your tests? How does it look like?
I don't understand it.
Do you write tests?
Yes.
So could you show me some?
Yeah, I can show you some tests offline after the talk.
Sorry.
Yes. The tests will be shown online,
Yeah.
offline? Is that
Yeah,
is that
we'll
right?
show them after the talk.
After presentation. Any more questions? Any questions from the audience?
Hi. At the beginning of the presentation, I saw something called context in the effect. So what is it?
Okay.
If it's what I mean it is, but
Let's see where it first comes up. Okay. So here within this continuation and within Kotlin we have the concept of a coroutine context. And the coroutine context in Kotlin is actually quite powerful, but you can use it for dispatching as well. So you can actually see it's similar to an execution context in Scala. It's not exactly the same, but it's similar to that. So if I go back here, this function, this creates a new single-threaded coroutine context. So it creates, if compared to Scala, it creates a new execution context that executes in a single thread. Shall we take a small break?
Okay.
Or?
Shall we take a small break before we start with the second part, which talks about arrow meta? 5 minutes? Thank you.
That was cool, man.
I was really nervous.
Can I get me water?
Yeah, that's great. Yeah.
All right. Shall we move on to the second part of our talk? That one is going to be a little bit shorter, but nevertheless, I'm sure it will be interesting. So let's give it a go.
Thank you. Can everybody hear me? Yeah? All right, great. So the second talk I'm going to do tonight is about ArrowMeta, which is a metaprogramming library for Kotlin. I'm going to skip the introduction because I hope by now you know who I am. But before I'm going to dive in any of the ArrowMeta stuff, I first want to dive into the Kotlin compiler, how it works and what it looks like. And I also want to thank our designers for the amazing animations and the amazing animations you also saw in the previous presentation. By no means I cannot do this. I have to ask our amazing designers, Isra and Jetro. And before the Kotlin compiler can do anything, of course, we had to write some code, as we saw in the video. So once we have written that code, the compiler can start doing something with this. So if you look at this snippet, it might look very familiar to the snippet that we saw before with FlatMap. And that is actually also, this is actually the comprehension that we envisioned for 2020 instead of the bang operator. So once that you have written the code, the Kotlin compiler can now read the code and parse it into an AST. And an AST is an abstract syntax tree, and Kotlin's abstract syntax tree is modeled after the program structure interface of IntelliJ, which is basically the tree structure they use within all of their tooling. And this Kotlin's AST is built upon this PSI structure of IntelliJ, which means that there's a lot of interrupt between the libraries written for JetBrains tooling and the same libraries that you can use for the Kotlin language. And once that this code is parsed into an AST, we go into the compiler goes into the analysis phase. And during the analysis phase, the compiler is going to try and enrich this model. And at this point, we can also already do type checking, or we could just let the compiler do its work, and it's going to resolve everything within that tree. It's going to enrich that tree with more information, and it's going to do the type checking, and it's going to create descriptors for us. And these descriptors can either be used by IntelliJ or the CodeGen phase to render tooling or to render the code. So once all this is done, and we've reached this step, our code is compiled correctly, or at least it has type checked correctly, because something can still go wrong during code generation, but that will mostly be due to bugs in the code generation, not due to something being wrong in your code. And Kotlin supports 3 platforms with JVM, JavaScript, and native. So in this phase, the compiler will generate the binaries that you want for your platforms. And after all that is done, your program is compiled and you have your binaries. So this is how the Kotlin compiler works. So now, ArrowMeta. What is ArrowMeta? ArrowMeta is something that works with the compiler. So in the Kotlin compiler is the concept of compiler plugins. And what we have essentially done is we've built a library on top of the compiler plugins to give us a more high-level way of working with the Kotlin compiler. So let's take a quick look at how this works. So once again, we start by writing some code. And once the code is written and parsed into the AST with ArrowMeta, we are going into the analysis phase. And as I mentioned in the analysis phase before, at this point we can do type checking. We are past parsing, so we have the AST. But we have not gone through actual type checking yet, and the compiler has also not created the descriptors yet for the CodeGen phase or IntelliJ. So at this point in time, or at this point in the compiler, we have implemented a quote system. And the quote system can basically traverse the tree change elements in the tree, and then pass it along in the compiler, and the compiler will just do its work as usual. So we can basically transform the tree that we have from the code and change it however we want. Once that is done, the compiler goes into the resolution phase with the type checking. And here's actually something really neat. I mentioned before that the Kotlin AST is built on the program structure interface by JetBrains. And what we can do here is we can create descriptors for IntelliJ for code that we have added to the tree. So the problem that we've seen in Scala or in other compiler plugin languages a lot in IntelliJ is that with new code or new generated code by the compiler plugins, everything turns red. And it's super annoying, it's not user-friendly. And the cool thing here is that we can automatically generate the support for IntelliJ. So by just writing your compiler plugin, automatically you get support for your tooling, which is an amazing thing because now you only have to write your code once, and we can reuse the code from the compiler plugin to work in IntelliJ for you. And then just like before, when everything is done, it goes into CodeGen, it generates the binaries for the platforms, and the program is compiled. So what kind of APIs and what kind of tools does Meta offer you to work with the things that I just showed you? Well, first of all, there's a low-level DSL. And how the compiler plugins work in Kotlin is basically, it works on a OOP-based system where you have to implement certain interfaces or abstract classes, and then you have to register them. We have hidden all that complexity for you, and we have created a functional DSL where you can just write functions, and we wire that logic up into the classes, and we register the extension in the compiler plugin for you, so we can do that all automatically for you. And what is really cool about this is the functional DSL is also composable. So for example, the update config function is something that the compiler plugins, functionality that the compiler plugins also offer. Same for the storage component, which you can use to inject different services into the compiler. You can compose different functions like the update config function, and you can create a higher level function, for example, in this case, enable ER, where we enable the ER generation of the compiler. I just realized I missed something. No, I can mention that later. So the low-level DSL basically offers all the APIs that you have from the Kotlin compiler by itself. And this list is way too long to cover, and I'm not going to cover it here. But it basically maps one-on-one with the API of the Kotlin compiler. So everything that you can find here, you can find there, you can also find here. But now let's move into the interesting part of Meta, the quote templates that I mentioned earlier. So the quote templates is something we can do. There's a high-level DSL that we can use to do meta transformations on our code. And in the arrow effects talk from before, we already talked about for comprehensions and rewriting flat map and do notation in Haskell. So here I'm going to show a little bit of the comprehension plugin that we wrote for Kotlin, which was a syntax that we've also already seen before. So first of all, I can very simply create a plugin by just defining a name and then defining a transformation. And here this transformation basically expects a list of extension phases. Like I mentioned before, there's a lot of phases you can extend to in the compiler or register to in the compiler after parsing, after analysis, before resolution, before CodeGen, all those kind of things. So here we just expect to give you a list of all the kind of work that you want to do for your comprehension plugin. And you can do that by opening a meta block. And within that meta block, we're going to open a quote. And this is the high-level DSL that I want to talk here about tonight. And this quote DSL takes a predicate. And that predicate is used to traverse the tree and select which element from the tree you want to transform. So in this case, I'm going to use a predicate contains fx block. which works on a kt.qualified expression. And a kt.qualified expression is basically just a function. So whenever you call io.fx, that dot is the dot qualified expression. So what we're going to look here for is code that contains io.fx. So that element is of the type dot qualified expression. And then what we get returned here, and actually it's dropping a little bit from the slide, is we get the original element from the tree, and then we can return a transformation. And the transformation that you can return here is basically any tree transformation that you can imagine. So you can replace a single element, you can replace an element with a bigger tree, you can remove elements from the tree. Any tree-based operation that you can imagine, you can also execute on the AST of Kotlin. So in this case, when I have found my comprehension block, I'm going to take the original block and I'm going to replace it with a rewritten to flatmap block. And I'm not going to go over all the code from the comprehensions, but basically this is what that looks like. And as you can see, I never have to sacrifice type safety either. I get a KT property and I get the remaining expressions in my comprehension. And just by that, I can very easily with a template write the code I want to rewrite it to. And this dot expression at the end will actually type check the template that I wrote as a string. So my code will be type checked before it continues, and we can return it as a typed element. So when you're working with these compiler plugins or with Arrow Meta, you don't have to work with string all the times. You can actually work with proper types that we know from this tree-like structure. And because it is, and it also interrupts with all of JetBrains libraries, which is awesome because so there's a big set of libraries that you can use in addition or together with Arrow Meta. And as I already mentioned, we think it's very important that you have good support for your editor. So alongside Arrow Meta or within Arrow Meta, we have also built a DSL for building IntelliJ plugins. And the reason that we do this is because we already use this to automatically generate the support for you. But on top of that, you can very easily add more support. For example, here I'm going to create an ID meta plugin, which I'm going to call the comprehension IDE plugin. And I'm going to add a line marker provider. That might sound very meaningless to you now, but I can also just show you a video of what that looks like and how that works. So here I'm writing my FX program. And while I'm writing my comprehension, on the left-hand side, an icon appears. So now it is clear to me that something special is happening there. And if the user goes over that icon, you can actually show him additional information. So if we go back to this slide, we can say, okay, I'm going to match on a KT expression, which is binding. And this is actually code that we've reused from the compiler plugin. So this is code that we've already written. And then we can just provide the user with a message and with icons. And this is a very extensive DSL for all the features in IntelliJ. But the goal here is we want to bring all these features to the editor. We want to guide people, write functional code in a very simple way by bringing them all the tools they want in the editor. So some of the plugins coming out in November, that might be delayed a little bit since it's already the end of November, but it's coming up very soon. That's all I'm going to say about it. So one of it is the higher kind of types plugin. And as some of you or all of you may already know, Kotlin has no support for higher kind of types, which is something that we love in functional programming, especially with our type classes. So this was something that we had to emulate in the past. And if you might just remember from the previous talk that in some places there was some weird syntax like fix that we had to do to downcast the higher kind of type and stuff like that. But now Arrow Meta can generate or add this code for you during compilation. And we can actually also cooperate with the type checker so that it is aware of your higher kind of types. So in this case, I don't have to call fix anymore, because I don't have to call fixed anymore, my type inference also improves. So in my opinion, this is a double win. Another one is optics. So optics is a very powerful concept in functional programming, and for some reason, a lot of people are scared away from optics. But with arrow meta, and this is actually that something already exists today, but with arrow meta we can make it so much more powerful. We can create a DSL that uses optics underneath that allow you to work with immutable data structures without requiring you to know anything about functional programming or optics. So if you're using copy and nested copies today, and you would like to have a more elegant solution, but you are not interested in learning any functional programming, you can even use this, which is a very powerful and advanced functional programming concept, and it's just put in a very elegant jacket. So, like I've already mentioned a couple of times today, comprehension, but something that I have not mentioned today is that the comprehensions will not be exclusive to Arrow or Arrow IO, but similar to Scala, the comprehensions will be enabled for any type that have a valid flat map structure. So you will also be able to use these comprehensions with Eric Java or Reactor on Spring or any other framework that has a valid flat map signature and a type that requires or binds you to that framework. And then another one, type classes. So Kotlin has no support for type classes or implicits. This is something that we were missing very hard, especially due to the boilerplate that it required us to write. So first of all, you were required to always explicitly pass the instances. And to enable the syntax, you either had to enable it to run, or you had to enable it through using an extension function and use the type class as an extension receiver. So in this case, we have added, with just adding the with keyword, the compiler plugin can inject the instance for you. And in Kotlin, we proposed Keep 87. Is anyone familiar with Keep 87? So Keep is a Kotlin enhancement evolution process where, similar to the Scala SIP, where people can propose new features for the language. 2 years ago, we proposed Keep 87 with type classes for coherent type classes, so not like implicits in Scala, but more like type classes in Haskell. So far, we have not gotten a response, so we've decided to try and prototype this with arrow meta, so people could already get a feel of what it would look like in the language. So, like I already mentioned, with this compiler plugin, you also don't have to explicitly pass the instances anymore, but the arrow meta or the compiler plugin will globally search for a coherent type class instance. And last and not least, I was heavily talking about suspend and side effect tracking in the previous talk. We're also working on a purity plugin, which will be both an IntelliJ and a compiler plugin. And this way we can help you in the editor to write functional code. For example, here, when you're writing a side effect, which is throwing an exception, we can detect that this function is not pure. And we can alert you of that, we can fail compilation, and we can even suggest refactoring tools to you, so you can refactor it straight from IntelliJ, and we can also give you additional information to why you should do this, or why this is useful. So join us and help us. Arrow Meta is still a very young project and has a lot of potential. Some things that we've thought about was union types, intersection types, type refinement, polyfunction macros. Feel free to reach out to me after the talk and discuss any of this. And some use cases that we think are really powerful and also not binding to functional programming per se is an automated refactoring tool like ScalaFix or Scala Steward, where they can automatically provide upgrades for version updates for your code base. Documentation tooling, so for the people familiar with that from Scala or Enc from Kotlin, where you have snippets in the documentation, we can actually make those snippets runnable. We can, through this IDE tooling, we can also make them interactable just like you were writing code but within their example. We can do type search engines like Google. A very interesting one is proposing keeps, like you would propose a SIP, but you can actually build a working implementation that people can try and play around with, like we are doing for the type classes, and many, many more use cases that you can do with Kotlin, with arrow meta, things that you can do with Scala meta or other metaprogramming languages. So I want to thank the compiler team and the community that helped us on Slack, on arrow meta, on the compiler and online proposals to bite through this huge chunk of undocumented compiler code. And I want to thank 47 for sponsoring, pushing the development of Meta. And I want to thank a special shout out to the people that helped bootstrap Meta. This was a very small group that got it to this point. And we can already, after the first announcement on Lambda World, we can already see an increase in contributors. So I hope to see some of you maybe in the coming weeks. And again, I want to thank everyone that made Arrow possible and Kotlin possible. And again, I want to thank the meetup for inviting me here and for everyone for coming. Thank you.
Thank you, Simon. So, questions? I would have a question, actually. So, from where I come from, like Kotlin is very, it's not a first language you would use for many sort of backend applications, and I wanted to ask, like, how does the Kotlin landscape look like in terms of tooling and support for, I don't know, build systems, continuous integration, etc. And how does Arrow Meta come into the picture, and
okay.
You know, how can that contribute?
I lost my microphone. That's okay. So Kotlin comes from JetBrains. So the tooling is, or at least the IDE is pretty amazing, and the tooling that you get there is pretty cool. The build system that is currently mostly used for Kotlin is Gradle, which is actually also adopting Kotlin. So you can also write Gradle scripts in Kotlin now, which also come with this awesome tooling in IntelliJ. So tooling-wise, it's actually pretty good. And having used Java and IntelliJ for quite a while, I would say it's definitely on par or even better than the Java tooling that's out there right now.
Okay, thank you.
Thank you, Simon. I wanted to ask, how hard was it to get started in digging into the Kotlin compiler and the stages and the documentation? Because usually this kind of, the compilers always have a lack of, let's say, documentation friendly.
Maybe we should discuss this over beer. But yeah, it was very difficult. I mean, it's a humongous beast, but most compilers are pretty alike. So once that you can figure out the phases, you can, after a while, you can start to pinpoint more things. But yeah, it involves hours and hours of debugging and seeing where everything goes and see how the code gets transformed. So it was an extremely time-consuming task. That's why I also wanted to do the special shout out to the people that went through all of this to make this possible.
One more question from me. So when I hear people talking about Kotlin, they mostly refer to it as like simplified Java or like more ergonomic Java. So, you know, if you take languages like Scala, Haskell, Kotlin, Java, what would be like strong argument to use Kotlin, leaving Android aside for a moment?
Okay, so I initially got started with Kotlin because it was a nicer Java. And that was the reason that I started with it. But seeing the language evolve, as I started using Kotlin around 0.7.8, and now it's 1.3.6, the difference between that is humongous. And if you can see the stuff that they're also planning into building into the language, it's very powerful. So I would say it's actually diverting more from the I'm a prettier Java stigma, and it's actually diverging more to I'm a very powerful language on myself. And I think we can also see that with the multi-platform stuff coming up. And I think they also have a very interesting multi-platform story. It's a very different story compared to Scala. I think it's a very powerful story. I think there's a lot of potential. And it's also rising on the back end. And we can also see players like Spring and other players moving towards Kotlin. And especially the biggest difference, I would say, is the compiler plugins. And this is also why you can see Android is building Compose, which is fully Kotlin, and it's heavily relying on compiler plugins and metaprogramming, which is something that you just can't do in Java.
Okay, thank you. Are there any other questions? Okay, so thanks, Simon, for great talk. Again, I appreciate that he came to us from abroad to present his thoughts on Kotlin and our library. So now the meetup is over, but there is a pub booked. It's a nearby pub, Kulna, if you know it. So those who are interested, we can carry on that with our talks and chats in the pub. Thank you. Thanks, everyone, and see you around.
Thank you, everyone.
Thanks, Simon.
My pleasure. It was my pleasure. Thank you.